Right, in this video I'm going to have a look at the rate constant K and how you calculate it, and once we've covered how you calculate it, we'll look at exactly what it is and why it's useful, and we're also going to look at the units for K. So this is a continuation of what I did in the last video. If you're not comfortable with how to work out what order something is, please go back and revisit the last video, although I am going to briefly recap it here. So I've got an example of a reaction, and the person has carried out this experiment 3 times, and each time that they have varied the concentration of one of the reactants and then measured the change in rate. So the first thing you need to do to calculate K is you need to work out what the order is with respect to each of the reactants, so NO2 and O3. I'm going to start by working out the order with respect to NO2. And in order to do this, I need to find an experiment where NO2 changes, but where O3 stays the same. And if I look at experiments 1 and 2, I can see that I am doubling the concentration of NO2. I'm going from 1 to 2, but the concentration of O3 stays exactly the same. So I know I'm doubling the concentration, but what effect does that have on the rate of the reaction? Now, if you're like me, you're not particularly great with standard form, it's not immediately obvious to me what's happening with those numbers. So what you can do is you can take the lower of the two numbers, the bottom number, 6.40 by 10 to the minus 8, and you can divide it by the number that is on top. Divide that by 3.20 by 10 to the minus 8, and you'll see that the answer is 2. And that tells me that to get from this number on the top down to this number here, I have to times by 2. So in other words, when I doubled the concentration, I also doubled the rate, and that is going to make NO2 first order. I now want to look at the order with respect to O3. So again, I need to find an experiment where where O3 changes, but NO2 stays the same. And in this case, I'm going to be looking at experiments 2 and 3, because NO2 remains the same, but O3 changes. And with O3, I can see I'm going from 2.5 to 5.0, so I can see I am increasing the concentration by a factor of 2. I'm doubling the concentration, but I need to look here and see what's happening to the rate. So again, not immediately obvious to me what's happening to the rate, so I'm going to take the number that's on the bottom and divide by the number that's on the top. So that's going to be 1.28 by 10 to the minus 7 divided by 6.40 by 10 to the minus 8. And I get an answer of 2. So that means going from here to here, I have increased the rate by a factor of 2. And because doubling the concentration doubles the rate, I can also say that O3 is first order. So once I have worked out the order with respect to both of my reactants, I am able to write myself a rate equation. My rate equation is rate equals K. My NO2 is to the power of 1 because it's first order. My O3 is also to the power of 1 because it is first order, and that is my rate equation. I can then rearrange my rate equation to solve for K. So K is going to be equal to, because it's multiplied on this side, I'm going to bring these two below the line on the other side. I'm going to have rate equals the concentration of NO2 and the concentration of O3. And then I just need to plug in numbers for my experiment. And it doesn't matter which experiment I choose. I can choose 1, 2, or 3. The only thing that matters is that you're consistently choosing numbers from the same line. So let's say I decide to choose experiment 1. All right. The rate in experiment 1 is 3.20 by 10 to the minus 8. The concentration of NO2 in experiment 1 was 1.00 by 10 to the minus 3. And the concentration of O3 in experiment 1 is 2.5 by 10 to the minus 3. So I plug in those numbers, I work it out, and I solve for K, and I see that K is 1.28 by 10 to the minus 2. So now I have calculated K. But what exactly is K and why is it useful? Well, K is what we call the rate constant. And unlike other constants, it changes depending on the reaction. So you've encountered the gas constant, or which is always 8.314. That's not the same for K. K is going to be different depending on the reaction that you are doing. And the only way to calculate K is to do the experiment multiple times. So you would have to go into the lab and repeat this experiment a number of different times. You would have to work out experimentally what the order was with NO2, what the order was with respect to O3, measure the rate each time, and do out this calculation, and you can eventually solve for K. But the useful thing about K is once you know it, it allows you to convert any concentration into the rate. So it's kind of similar to an exchange rate in that regard. If you know the exchange rate, let's say that €1 gets you 80p. Once you know the exchange rate, you know how much €1 is in pounds, you can then work out how much €100 is in pounds, or how much €200 is, or €300 is. As soon as you know that exchange rate, you're able to convert any number of euros into any number of pounds. And it's the same with K. As soon as you know what K is, you can take any concentration and you can work out what the rate will be without actually having to go back into the lab to work the whole thing out again. So if I look at my original rate equation, once I know what K is, I can plug in my value for K, I can plug in any concentration I want for NO2 and O3, and I can work out what the rate will be. And that's valuable because it's going to save time. Doing these experiments over and over again is quite time consuming and it's quite costly, but once you know K, you can plug in any concentration for that reaction under the same conditions, and you'll be able to work out what the rate is without going back to the lab and doing the whole experiment again. Okay, and that's convenient. So that is what K is, but you have to first work it out by doing a couple of the experiments. Once you know what it is, you can then always go from concentration to rate, and vice versa. Okay, the only thing we need to be able to work out is units for K, okay, and I'll fill that in here. So if I go back to my original equation here for K, so I'm going to shimmy up a little bit here, we'll see that this number here represents the rate. What is my unit for rate of reaction? Rate of reaction is always moles per decimeters cubed per second. So the change in concentration over time, moles per decimeters cubed per second for rate. On the bottom line, I've got concentrations, and my unit for concentration is just mole per decimeters cubed. So for NO2, I've got mole per decimeters cubed, and for O3, I've got mole per decimeters cubed. So I'm just plugging in the units for my rate equation, and now I need to solve for K. So I've got moles per decimeters cubed on the top line. That will cancel with the moles per decimeters cubed on the bottom line. So those two will just immediately cancel each other out. And that leaves me with seconds to the -1 on the top and moles per decimeters cubed at the bottom. What I'm going to do is what's on the bottom line, I'm going to bring to the top. And when I do that, when I bring these values above the line, I have to change the sign in the power. So at the moment, moles is just to the power of 1. When I bring it above the line, it's going to be moles to the -1. The moment, dm is to the -3. When I bring it above the line, it's going to be dm3. And that's now my unit for K. Now it's common convention to write the positive first, so dm3, although you won't be marked down for doing that. And then beyond that, it doesn't matter what order you write them in. dm3 mole to the -1 second to the -1. So I've got a few other examples here that I'm going to go through with you, and then I'll get you to do a few of them for yourself. So the first one I've got, if I look at the rate equation, is rate equals K, A, and B. So if I'm solving for K, I'm writing K equals rate over the concentration. Actually, well, I'm going to change this, or else it'll be the same as the one I've just done. And B squared. So that's my rate equation. And then I need to fill in my units. My unit for rate is always moles per decimeters cubed per second. And then on the bottom line, I've got concentration of A, which is moles per decimeters cubed. And I've got the concentration of B squared, which means I'm going to have moles per decimeters cubed twice. We've got 3 of them now on the bottom. The bottom will cancel with the top, so I'll get rid of that moles per dm cubed at the top. But I need to simplify my bottom line a little bit more before I bring it above the line. So when I'm multiplying with indices, what I do is I add the numbers. So I've got mole to the power of 1 each time. So I've got mole, 1 plus 1 is 2, so mole squared. And then I've got dm minus 3 and dm minus 3. minus 3 is minus 6. So I can simplify that. And once I've got it simplified, I'm going to bring the bottom line to the top. And when I do that, I need to change the sign. So my moles squared becomes moles to the minus 2. And my dm minus 6 becomes dm plus 6. And then again, it's just common convention to write the positive integer, or sorry, the positive index first, but you don't have to do that. I'll just do one more that works out a little bit different. I'll do that one, and then I'm going to give you some questions to do. Rate equals, k to the a to the power of 0. So if I had a 0 order reaction, all right? In this case, we've seen already that I can simplify this. Anything to the power of 0 is 1, so rate just equals k. And if k just equals rate, the unit for rates is moles per decimeters cubed per second. So the unit of k just becomes moles per decimeters cubed per second, and that's going to be your unit. I'm going to get you to have a go at one of two questions. Let me find one that you can do. So have a go here at exercise 3, question number 1, and then I'll go through the answer with you. So you've got all of the data. You need to work out the order with respect to A and B. So look at the change in concentration and see how that affects the change in rate. Once you know the orders, you can add them up for the overall order and write yourself a rate equation. And then you're going to pick one experiment, either 1, 2, or 3. Plug the numbers into your rate equation and calculate k, and once you've calculated k, you can have a go at determining the unit. So press pause, have a go at that question, and press play when you're ready to see the answer. Alright, I'm going to run through the answer. State the order with respect to A. So I need to find an experiment where A changes and B stays the same. That's going to be experiment 1 and 2. And if I look at 1 and 2, I can see that A is increasing by a factor of 2. What happens to the rate? So again, it's not obvious to me what's happening in standard form. So I take my calculator and I put the bottom number in first, which is going to be 2.16 by 10 to the minus 3. Divide that by 5.40 by 10 to the minus 4. So bottom divided by the top, and I get the answer of 4. And that means as I go from experiment 1 to experiment 2, the rate is increasing by a factor of 4. So if I've doubled it, and the rate increases by a factor of 4, then A is going to be second order. Now I need to work out B. I need to find an experiment where B changes and A stays the same. So as I go from experiment 2 to experiment 3, A is staying the same and B is going from 0.2 to 0.3. So B is increasing by a factor of 1.5. And again, if you can't see that, all you need to do is do the number at the bottom, 0.3, divided by the number above it, 0.2, and you'll see that you're getting 1.5. So don't let the numbers throw you off. I then need to see what's happening to the rate as I go from experiment 2 to experiment 3, and again I take the number at the bottom, 3.24 by 10 to the minus 3, and I divide it by the number at the top, 2.16 by 10 to the minus 3, and I see that it also increases by a factor of 1.5. So if I increase the concentration by 1.5 and I also increase the rate by 1.5, then B must be first order. The overall order is therefore 3. When I write my rate equation, it's rate equals k, A to the power of 2, and B to the power of 1, and I don't need to include the 1. They then ask you to calculate k, and I've told you you can use values from experiment 1, 2, or 3. So it doesn't matter which experiment you pick. You're going to pick, if I picked 1, I'd pick 5.4, and I'd fill that in for rate. For A, I would fill in 0.01, and for B, I would fill in 0.2. So I've done that over here. I've used the results from experiment 1, but you can use any experiment. I plug all the values in, I rearrange to solve for k, and I end up with k equaling 27. So I brought these numbers over here, solved, and worked out that k was equal to 27. Once I've worked out k, the last thing they asked me to do is determine the units. All right, so the number that I've got here on the top, remember this is the rate, and if it's rate, the units are mole per decimeters cubed per second. On the bottom, I've got mole per decimeters cubed, and it is squared, so I've got 2 of them, and I've also just got one that is just mole per decimeters cubed. The one at the bottom will cancel with the one at the top. Okay, I need to square my bottom line before I bring it above. So I've got moles squared. And then again, if you are multiplying indices, you are adding the numbers together. So it's minus 3 minus 3, which is minus 6. Okay, so I'm not, well, yeah, you are, well, I'm not doing minus 3 times minus 3. I'm not timesing it by itself. I add the indices. Minus 3 is minus 6. And once I've got that done, I bring the numbers above the line. And I'm going to get dm6 and mole minus 2. And again, it doesn't matter the order that you write those units down in. So these questions are effectively done the same way, okay? And there's lots of sample questions in your booklets. My advice would be to do all of them because they are important and they do take a little bit of practice, especially if you've got a reaction where you've got, you know, a couple of different reactions like I've got here, X, Y, and Z, and they've got 4 different experiments. It'll take you a minute to see which experiments you should use for each of your reactants. So for example, for X, I need to find one where X changes, but Y and Z stays the same. That's going to be experiment 1 and 2. And again, I can see I am doubling the concentration. And then to find out what happens to the rate, I do 1.06 by 10 to the minus 6 divided by the number above, and I'll find out what's happening with the rate. If I was worried about looking at Y, I need to find one where Y changes, but X and Z both stay the same. So that would be experiments 2 and 3. So if I go from 2 to 3, I'm doubling the concentration of Y, but there's no change to X, there's no change to Z. To find out what happens to the concentration, I'm going to be 2.11 divided by the 1.06 to find out what happens to the rate at the same time. And then if I'm looking at Z, I'm going to need to use, let me see, what will I use? Oh, I'm going to have to use 1 and 4. So going from 1 to 4, I am doubling the concentration of Z, but my X stays the same and my Y stays the same. And then to find out what happens to the rate, again, I'm taking the number on the bottom, which is going to be 5.28 by 10 to the minus 7, dividing it by the first experiment, 2.64 by 10 to the minus 7. And I see that as I double it, my rate increases by a factor of 2, meaning it is first order. So just make sure you are comfortable working out the orders. Once you've got the orders, you'll plug it into your rate equation and solve for K. Remember, you can take any experiment to solve for K. Just make sure you're taking all of the numbers from the same line, and then you will calculate the units. Again, the questions, they don't differ all that much year on year, but they do require some practice.